All right, hey everyone, welcome back to our series on linear algebra. This is actually take 3 for recording this video. I my Wi-Fi went out twice, and both were in the sequence of trying to record this or in the process. So third time's a charm, I hope. Let's dive in. This is section 3.3 in the textbook. It's all about matrix inverses. We're going to break it up into two parts because the whole section is rather long, and we introduce a lot of new ideas. So this time we'll just go as far as like introducing elementary matrices, and then we won't do anything with them. Okay, great. So the motivation for the need for an inverse of a matrix is the following matrix equation. If you have AX equals B, that looks an awful lot like standard issue linear equation in a single variable, AX equals B. And if you're going to solve this easy guy, well, what are you going to do? You're going to divide both sides by A. But I want to change your perspective a little bit to, instead of dividing both sides by A, think about multiplying both sides by the multiplicative inverse of A. What do I mean by that? If you remember, the multiplicative inverse is like the reciprocal. So, or you raise it to the negative first power. So in other words, we do like a to the negative 1 times ax equals a to the negative 1b. And then whenever you multiply, 1/3 times 3, you always get 1. That's what's happening here. That's why we multiply both sides by the multiplicative inverse. Except it's like dividing both sides by a. The idea is it will cancel on one side and reappear inverted on the other side. Okay? This is a general solution to this equation. If you have ax equals b, then obviously x equals a inverse times b. So if I have a matrix equation, ax equals b, with vectors x and b and matrix A, then I should be able to do something similar for some multiplicative inverse of a matrix. Maybe if the matrix A satisfies some properties. So let's take a look at that. So we have to define what do we mean by an inverse? Well, we need a matrix. So you start with a matrix A. We're always going to be dealing with an n by n matrix because we don't stand a chance for a matrix to be invertible otherwise. We'll see that in a moment. Then we define n inverse of A to be another n by n matrix such that if you take we'll call it A prime, and if you we want it to satisfy the property that A times A prime will be the same as A prime times A, and both of them, when you multiply them together, you get the identity matrix. Just like when you multiply two multiplicative inverse numbers, which are multiplicative inverses of one another, you get the multiplicative identity 1. Same for matrices, except it's the identity matrix that you get. We call it, we say A is an invertible matrix if you can find an A prime that satisfies these properties. Notice we're calling it an inverse of A. There's no guarantee that such an inverse is unique. It's unique for real numbers, but we always remember our rule of thumb is that matrices don't always behave like real numbers. So at the very least, if we want A to have an inverse, it should satisfy this property. Okay, let's just see an example of that. So if you have 2, 5, 1, 3, this matrix, then and you have a second matrix, 3, -5, -1, 2. If you check by matrix multiplication, which we've talked about, both times you'll get the identity. Okay, and I'll just check one coordinate. For example, when you're computing A times A prime and you want to get this 1 in the top corner, take the first column of A prime and the first row of A, multiply them together. 3 times 2 is 6. -1 times 5 is -5, and 6 minus 5, sure enough, is 1. Right? You'll have to believe me for the other ones unless you want to check it yourself. Okay, great. However, not every matrix is invertible. Zero, as far as a number goes, like the number zero, does not have a multiplicative inverse, right? Well, here is a matrix, the zero matrix, and sure enough, it does not have a multiplicative inverse. Think about it. Just take any matrix and multiply it by the zero matrix. You're going to get the zero matrix, and so you're not going to get the identity, right? Whether you multiply on the left or the right, no chance. Here is a non-zero matrix, 1, 2, 2, 4, which also doesn't have an inverse. And we will talk about why that is, but I will not tell you. But just know that non-zero matrices could still fail to have a multiplicative inverse. Okay, but let's deal with, first of all, before we talk about how to figure out whether this matrix has an inverse or not, we should talk about the uniqueness of the multiplicative inverse. We do have a theorem which says that if A is invertible, then its inverse is unique. Okay? Well, the proof is pretty straightforward. Suppose that there were two. Okay. I should say something about this proof technique that we're about to employ. To prove uniqueness in mathematics, we assume that the strategy is always the same. We just assume that you had two things that satisfied the thing that you're trying to prove is unique, and then you have to show for some reason that one is equal to the other. Okay, so we're just going to call our two candidate inverse matrices A prime and A double prime. Just to remind you, A double prime, this is a spoiler alert. A prime times A is the identity, and A times A prime is the identity, and same for A double prime. That's what it means for these things to both be inverses. Both of them satisfy these equations. So now what we do is we take a good look at A prime. Okay, well, A prime is definitely A prime times the identity, right? But the identity, because of this equation satisfied by A double prime, we can write this as A prime times A double prime. But by associativity of matrices, this is A prime times A double prime. That's the associative property. And by this first equation, notice this is just the identity times A double prime, which is just A double prime. At no point did I need matrix, like the commutative property of matrix multiplication. All I did was the associative property, and I leveraged twice the fact that A prime and A double prime are inverses. But notice, that means A prime is equal to A double prime. And so we're done. Okay, so in other words, the inverse is unique, and we can call it the inverse. So for notation purposes, we call it A to the minus 1, and we say A inverse. Okay? So now to put your minds to rest about what we were talking about earlier, suppose you have an n by n invertible matrix, and you have the system AX equals B. Then the unique solution to that system of equations is precisely A inverse times B. It's exactly the thing that we wanted. So let's prove it. First of all, I have to prove to you that this is a solution. That one's easy, because you just plug in X equals A inverse B into this system. In other words, first of all, okay, notice that if you just do dimension counting, A inverse is n by n, and B is n by 1. Matrix multiplication says that we're allowed to multiply them, and the dimensions of the output are n by 1. So it's a column vector, this thing that we've done. Okay? So the dimensions work out. And so we can also plug it in for x. In other words, ax equals b. This is the same as saying a times, let me erase our scratch work, if you can call it that, A times A inverse B. Well, let's just do this. We can just simplify our work. What actually do we get? AX when we plug in this thing for x? Well, it's A times A inverse B, which is just by associativity, A times A inverse times B, which is the identity times B, which is B. In other words, when you plug in A inverse times B for x, the output is B. Now, how do I know that this is unique? Well, so for uniqueness, suppose y satisfies ax equals b. Some other solution, yeah? Then ay, of course, equals b. But if you multiply both sides of this equation on the left by A inverse, you have A inverse times AY equals A inverse B. Associativity, and then the property of the inverse, and then multiplication by the identity on the left all tells us that Y is A inverse B, which is precisely X. In other words, they were the same, right? Great, that's it. That's all there is to it. Okay, we do have another theorem back to back. This one is about, okay, so we know that all the equations are satisfied and everything else, but now we have to ask, how do you actually go and compute the inverse? So the inverse for a 2x2 matrix is way easier than for other matrices, but I will start with this for now. So suppose that you just, we'll do it for any matrix that's invertible, or we'll show that's invertible or not. So suppose that A is just an arbitrary ABCD matrix. Then A is invertible if this number, AD minus BC, is non-zero. And if you want to compute the inverse, you do 1 over that number, AD minus BC, and then you multiply that scalar times this new 2x2 matrix, which is it's D negative B negative C A. So what you do is you take the original matrix A, and you switch the two numbers on the top left and bottom right corner, switch their position, and then the other two numbers, you switch their sign, but you keep them where they are. Okay? We'll look at an example in just a moment. But notice there it's a little bit stronger than that. If you have AD minus BC is equal to 0, then the matrix is not invertible. Okay? That number AD minus BC is called the determinant of A. I say that now as a foreshadowing. We won't go into it right now, but we will talk about it later on. Determinant of a square matrix. Well, anyway, so what you do is you compute this number, do 1 over it, and then multiply it by this transformed matrix. To prove that this inverse exists, is unique, and only happens when you have AD minus BC is not equal to 0, the proof is pretty long. But the book does go through the whole thing. I'm not going to do it here, but the rough sketch of it is you compute A times A inverse times A. Then you have to set up a system of equations, assuming that AD minus BC is equal to 0, and show that it has no solution for that last part to show that A is not invertible. It's a long proof. Okay, but this is more of a computational algorithm anyway, right? And so we're not going to go into the proof for this one. But notice, okay, so let's compute, first of all, the inverse of 1, 2, 3, 4. I feel like that matrix is our friend by now. Okay, so let's compute its inverse. 1, 2, 3, 4 inverse is, well, what do? We switch the numbers on the main diagonal. Oh, first of all, we have to do compute AD minus BC. So, oh, by the way, to remember that, just do like this. AD minus BC. I always draw that symbol when I'm doing a determinant of a 2 by 2 matrix in my head. 1 times 4 is 4. 3 times 2 is 6. 4 minus 6 is negative 2. So 1 over negative 2 times, and then what do we do to the matrix? Well, we switch the 4 and the 1, and you switch the signs of the 2 and the 3. So negative 2 and negative 3. We keep them in place. And then 1 over negative 2 means negative 1/2 times all of these numbers. We can do that. It'll be negative 2, positive 1, positive 3 halves, negative 1/2. And you should check that this matrix multiplies with 1, 2, 3, 4 to get the identity. Okay, great. And now let's just take a look at this other guy. You know, if we're going to give an example, we're going to give a non-example. So 1 times 6 is 6, and 2 times 3 is also 6, and 6 minus 6 is 0. So there's no inverse, or not invertible. That's it. Conveniently, we can also solve this system of equations just easily. Remember, so this is, I'm going to write it as okay. This is going to look like more work than just like normal solution techniques, but that's because I'm showing a whole lot of steps here, which is going to be funny because it's like a one-liner, even still. Okay, I'm going to write this as the matrix equation. It's 1, negative 1, 1, 1, augmented with, okay, times xy equals 5, 3. So xy is 1, negative 1, 1, 1 inverse times 5, 3. The inverse of this matrix we can compute in our heads. It's going to be, well, AD minus BC is 1 times 1 minus negative 1 times 1, which is 1 times 1, which is 1 plus 1, which is 2. So it's going to be 1/2 times the thing that you get when you switch the things on the main diagonal and switch the signs of the off diagonals. And then multiply everything by 5, 3. We're going to do the multiplication before scaling. So it'll be 1/2 times the column vector 5 plus 3 is 8, and negative 5 plus 3 is negative 2. Uh-oh, we're going to run out of Apple Pencil battery. Nice. Which is, this is 4, negative 1. Okay. Great. So now I just want to start talking about some properties of inverse matrices. Right, so this is theorem 3.9 in the book. These properties are convenient, although one of them is interesting. They're all interesting, but okay. So we'll just go through them. So if A is an invertible matrix, then, well, its inverse is also an invertible matrix. And by the way, the inverse of the inverse is the original matrix, right? A inverse is just A. Also, if you have a scalar times a matrix, that'll give you a new matrix. And we ask, like, what is its inverse? Well, its inverse, you might think it's just the scalar times the inverse. It's actually 1 over the scalar times the inverse, which is surprising. And you might think, well, what if the scalar is 0? Okay, well, then you're asking for the inverse of 0 times A. That's asking for the inverse of the 0 matrix. And we already know that one doesn't have an inverse, right? So we're not going to run into a divide by 0 error, this part of the theorem, that's for sure, right? This third one is very similar to what we saw about matrix transposes. It says if A and B are invertible and of the same size, then the product AB is invertible, and its inverse is the product of the inverses in the reverse order. So in other words, AB inverse is B inverse A inverse. The order is switched again, right? Okay, that was like what happened with the transpose. Speaking of transposes, if A is invertible, then its transpose is also invertible. And this is strange. The inverse of the transpose is the transpose of the inverse. So like transpose commutes with inverse. That's surprising. Okay, and then the last one is that, okay, if A is an invertible matrix, then A raised to any power is also an invertible matrix. And the inverse of A raised to that power is the same thing as if you were to take the inverse of A and raise it to that power. It's interesting. Again, seems like the number commutes the exponent. Okay, we're going to prove the third one. But this is going to be kind of boring. Okay, we just have to show. So notice, by the way, right, we just have to show that if X is equal to this matrix, B inverse A inverse, then it satisfies the property of being an inverse. And if it satisfies the property of being an inverse, that inverse is unique by the theorem that we just saw. So in other words, we just compute AB, I'm only going to do one direction, times B inverse A inverse. Well, by associativity of matrices, this is A times B inverse times A inverse, which is A times I times A inverse, which is just A inverse, which is the identity. Okay, switch the order, do the same thing. The A inverses will cancel first, then the B inverses will cancel, back down to the identity, and we're done. Right, then B inverse A inverse satisfies the property of being an inverse for AB, which means that it's unique. Oh, by the way, we have, this is kind of a cool matrix equation type thing. So if A is an invertible matrix, that fifth part of our theorem lets us give the definition for A to a negative power of the matrix. And yeah, what you do is just compute the inverse and then raise it to that power. Or if you prefer, raise the matrix to the power first and then do its inverse. Consequence is that matrices satisfy all our laws of exponents. You can add and multiply exponents and stuff like that. So let's solve. Okay, so solve this matrix equation for X, where X is like a matrix, and we're assuming, by the way, assume throughout that like these matrices are of the appropriate size. They make sense, right? Because like otherwise, what are we doing, right? Probably just assume everything is n by n. Okay, great. So doing that, let's take a look. A inverse times bx inverse is equal to A inverse times B cubed whole squared. Okay, well, I'm going to just copy paste that because that's faster than writing it again. And now what can we do? Let's multiply A on the right, of both sides, A on the left of both sides. So A inverse is just the identity. So we can write the left side as bx inverse. And on the right, that's going to be A times A inverse B cubed squared. And instead of writing squared, I'm just going to write it everything out. A inverse b cubed. Why? Because I'm about to have to take the inverse of both sides. I'm not going to do that yet. First, I'm going to use, notice I can use an associative property to well, let me duplicate, copy both sides, because, you know, I want to show our work in as much detail as possible. So, by the associative property, I can swap these things around, and then they cancel. They become the identity. So I'm just going to cancel them out entirely. Okay, now I'm free to invert both sides. So what I'm going to do is raise both sides to the -1. On the left, the inverse of the inverse is the original. So bx inverse is just bx. And on the right, we have to be careful. I'm going to drop the inside parentheses because after all, the associative property says I can multiply these in any order as long as I'm not switching the left to right order. I can pair up any product of them. And then, okay, the property that we proved in the previous theorem says that if I'm going to invert something, I have to switch the order. So this guy is like b cubed. So the inverse of this product of three matrices is start with this guy, invert it, so b to the -3. Then take this guy and invert it, so just a. Then take the third guy and invert it, so b to the -3 again. Notice I worked backwards. I worked right to left, but I wrote them left to right. Because remember, taking the inverse switches the order of multiplication. Very, very important little subtlety that will definitely get you at some point, or at least it'll try. Last step, by the way, is to multiply both sides by b inverse on the left. So x equals b inverse times b to the -3, which is b to the -4, a b to the -3. Has to be on the left. It can't be on the right because like matrix multiplication does not commute, right? Okay, final answer. A lot of properties going into this one. Okay, now we're going to end this video with a definition. So we're going to define elementary matrices. And these are great. These matrices are very friendly. So an elementary matrix is a matrix where multiplying it on the left of another matrix does a row operation to that matrix. Okay, so here's our elementary matrix. It looks suspiciously like the 3x3 identity matrix. Here's just some random matrix A that very importantly has 3 columns or three rows. So this is a 3x2 matrix. This is a 3x3 matrix. Its product will be a 3x2 matrix. And notice when you multiply them, you can check the multiplication if you want. It's very straightforward. You get a matrix that's almost the same, but the difference is that the bottom 2 rows switched places. Now, what's awesome is that the matrix that you multiplied by was the identity matrix. The bottom 2 rows switched. That's all it was. So we did a row operation to the identity matrix, then multiplied it, identity matrix of the appropriate size. Then we multiply it by A, and it did that row operation to A. Yeah, and in fact, that's where the definition comes from. An elementary matrix is just a matrix that can be obtained by doing a single row operation on the identity matrix. This is a way of formalizing row operations to, instead of trying to do like linear combinations of rows or something like that, no, we're just like multiplying by a matrix. Okay, so let me give you some examples of what an elementary matrix will look like. First of all, you can have a number times any one of the entries on the like on the diagonal of the elementary or of the identity matrix. Whichever row or whichever diagonal entry that you have, which is not the number one, will correspond to scaling that row in your matrix A by the number one. You can, of course, switch two entries. So in the second example, that's just row one and row two switched. And in the third example, we have what it looks like to add -4 copies of row two to row four, right? We just take that thing, multiply it by -4 and add it downward. So this is also an elementary matrix, and its effect will be to do the corresponding thing to A. And theorem 310 is just saying what I just said. Yeah. If E is an elementary matrix, then EA is the matrix obtained by performing the corresponding row operation of E on A. Another awesome thing, now you remember that row operations can be reversed. Well, that's the same as saying elementary matrices have inverses. In fact, every elementary matrix is invertible, and the inverse of that matrix will be another matrix of the same type. Okay, so to leave you as a total cliffhanger, if you can row reduce a matrix to the identity matrix, that means there's a sequence of elementary matrices that you can multiply on the left of A by to get down to the identity matrix. And then you have to ask, well, what if I were to multiply the identity matrix by that thing? Or like what if I just multiply those things together, but then don't multiply by the matrix A that I'm trying to row reduce? What matrix will pop out? What is that new matrix? Turns out that will be the inverse, and that's our pathway to computing the inverse of an arbitrary matrix. However, we're going to do that in the next video, so I will see you there.